It's actually the last quarter, right, 3 months. His first project as he joined was deep learning, and he has some goodies that he can show. And we actually have some good news. It actually runs at customers, which is good. Some of them were here earlier, and we're very excited. You'll see Arno talk about it. Arno himself is, how many of you have heard of H2O? This is probably the first time some of you are hearing. So it is a machine learning framework. We want to build Google scale machine learning for enterprise. So it's actually Google, like all similar mindset of building high scale engineering, but machine learning is what we are offering as what you can take it, plug it into your enterprise app. Our vision is to power smart applications. We think every application needs to be an intelligent application. Every one that we have seen in the last 10, 20 years of creation needs to go through a machine learning phase, and then you have intelligent applications that will power the future. So towards that, deep learning is an amazing algorithm. Some of you have heard of it from Jeff Dean's and Jeff Hinton's work. My first work with neural nets was 20 years ago. It's kind of fun to watch myself build a company that's actually doing neural nets, and it's kind of really rare to have someone of the talent of Arno come build it for us and for the rest of the universe, because it is Apache V2 license. The other interesting thing about Arno, he spent 7 years in Stanford Linear Accelerator, SLAC, where he actually has a very cool, on his website, has a very cool how, you want to explain how the go through the, like, really cool physics, right? And we always wanted physicists. I think that you've seen data scientists and we've talked about mathematicians, but I think the world belongs to physics, really. And that's kind of the harbinger of the future. Hopefully we'll have more physicists, any physicists in the audience. Please come talk to us, because that's what I call as the domain science. Data science will lead to domain science. So a year from now, you probably see us talking about Silicon Valley big domain science, right? So towards that, this is kind of the beginning of things to come. Physicists will come and take a rightful position in the overall scheme of things. Without further ado, I want to let Arno take over and present us deep learning, and there'll be some fireworks, some demos.
Definitely, yes.
Perfect.
All right, thank you, Shane.
Thank you.
So here, yes, 6 years at SLAC, 2 years at Skytree, so that was another machine learning company, so I have a little bit of a background in machine learning as well. Mostly HPC, C++, and now here Java. So Java is new for me, so I did all this in Java, which I never did before, except for maybe 1 month or so. So this is this shows you how easy it is to program in H2O, because if I can do it with no Java experience.
Or how good a programmer he is.
Just So, great, yeah, so obviously your neurons have worked. You found your way here. I'm going to tell you how we use our artificial neurons to make models that are hopefully smarter than random luck. And you'll see that that actually works fairly well. I'll first show you what H2O is about, then I'll show you what deep learning means. That's the theory behind neural nets. And then there will be some results on MNIST. Who knows what MNIST is? A couple hands up. Good, great. That's a standard, right? And then there's Prostate, another standard. But then there's also some eBay dataset, which is actually the real dataset. All right, so H2O is a distributed math platform. Parallel and distributed doesn't need a whole lot here, but I guess can't have too much of something good. It's multi-threaded and distributed across machines. Everything is meant to be using all the cores that you have in your system. And when you put these math building blocks together, you get good algorithms for generalized linear models, for random forests, radial boosters, trees, and so on. You'll have principal component analysis, all kinds of stuff, k-means, and now also deep learning. So there's a lot of applications you can actually satisfy with these algorithms. And especially since our SDK API is super easy to use. You have Java, of course, you have access to all the methods to R, you can program in Scala, there's Python wrappers, everything connects to JSON, REST API, right? So this whole thing is meant to be enterprise grade. And businesses can use all the data because this scales to big data. It's meant for big data. So it's the platform that came first, and then we put machine learning on top. So more data gives you better algorithms. More data and better algorithms gives you better predictions. So the team here, a little less than 20 people. Everybody's an expert in their field, really great team to work with. And we do all our stuff directly in GitHub. So everything I push is immediately visible to you, everybody in the whole world. Pretty good concept. There's no secrets. We have a great team of advisors. They wrote literally the books on machine learning, on optimization, on Java. People here, Cliff wrote JVM, JIT, and I encourage you to listen to his talks. Tells you what this framework is about. And of course, Sri with the great mindset of what it takes to bring this to the masses. We're doing this right here. So this is exciting times. So H2O runs on Hadoop. It runs also without Hadoop. It does MapReduce, but not Hadoop's MapReduce. So there's all these things that you can see, building blocks. HDFS is the data storage that many people use. We can suck in the data no matter whether we run alone without Hadoop. We can just connect to an HDFS server, or we can actually sit inside Hadoop, either with Yarn now or with the old MapReduce, and you get launched as a MapReduce job, which just sits there and waits and waits and waits and updates some counters from time to time so it doesn't get killed. But it doesn't really use the MapReduce paradigm of the Apache MapReduce. It does its own MapReduce in memory inside. So it's super fast. And like I said earlier, it connects to all these languages so you can do whatever you want.
Excuse me.
Yes?
So do you, you said you just sit on top of HDFS, so do you keep the data locality and fault tolerance that Hadoop offers actually, or just the way you work with
We
data?
have the fault tolerance of HDFS,
Okay.
because we say give me the data and hopefully the data is there.
Right, but
If
local
our job
data-
gets killed because one of the nodes goes down, then the job is gone. So we have throwaway clusters of in-memory compute, basically. We don't have a redundancy built in the system yet.
Sure.
But we actually have a design for that as well. It was already planned in the beginning, but we don't really need it right now because people usually run this on like 20 or 50 so nodes. And the chances that those go down are relatively low. It's easy to just run another one. You don't want to have a factor 2 slowdown all the time just because once a year one machine goes down.
Sure.
It's not yet big enough, but it's definitely doable. That concept of redundancy is
Sure. And how about data locality? So you push, I mean, you push computation to
We
data
found
or
that the network. So we went into first generation before the Arno joined.
okay.
We actually had a data locale aware, name node aware, like ingest of data.
Sure.
It saved us no performance. Basically, removing the data from the disk is your biggest performance bottleneck. Network is not your problem. So that's kind of what we found was we spray the data evenly and then balance it very efficiently.
Sure.
Yeah, one quick question. So you support like HDFS, that's a single point of failure. So name node, so version 1 has only
Correct.
one name node, the second one has backup, but still it's not a complete solution here.
We support MapRFS, Cloudera, or
Yeah, I think Napa has a solution. Yeah.
any of them. So
Other-
if you're worried about name nodes, then you should look at that as well.
Yes.
Just a quick question. So if it's in memory, then is it sort of like Spark or like HANA kind of thing? Or?
similar, yes, but not exactly.
We're purpose-built for quantitative.
Okay, this is pre-Spark thing.
So yes, you can stack your data in from flat files, from S3 or from databases, whatever you have somehow that you get data from. Often it's HDFS. This goes into our KV store that's in memory. So any way you put it in, everybody knows it's in. So it's an atomic update of a distributed in-memory database. And Cliff literally wrote the algorithm that does this atomic update on the hash data. So that's very powerful. That leads you to have this nice storage system in the back end where you can put stuff in, take stuff out, and do this all super fast. So we can do MapReduces fast. Everything is compressed on the fly. So when you suck in data, you compress it, and later when you need it, you expand it, and you decompress it on the fly, which means you're not wasting memory bandwidth to send over a double just to say it's a 1 or a 2 or something, right? You can compress it things. So you're going to have some more space.
One more chair there.
Maybe you can stand in that corner there. There's some space in that corner. There's no chair. There's one here actually. Actually, next time I'll probably draw an arrow here too, because the machine learning algorithms that talk to this in-memory KV store, but this whole thing is able to be accessed through an API, right? So there's an R engine, you can type in commands as if it's in R, and R will actually talk to H2O and say, oh, it's too big for me, I'll let you do it. So the cluster does the work, not R, but you can control it from R. You just load one module in the beginning that's called H2O, and you're good. So it's pretty powerful stuff. This is a way to do scalable R. Then there's a way to export the models that we predict, that we make. The models you can actually export as Java code. So it means later you have a Java code that says if number bigger than 3, then this, else, this, and that, and it's all super fast inline. You can just use it and deploy it, and that gives you a nano-fast scoring because there's no memory, no heat, nothing. It's just numbers in the registers in the process. And of course, you can do all kinds of analytics if you have this. For example, deep learning, which we'll focus on later. So what is deep learning? Wikipedia says it's a set of algorithms in machine learning that attempt to model high-level abstractions in data by using architectures composed of multiple nonlinear transformations. So you do something again and again, and somehow that original data is now suddenly a little different. And hopefully you see the structure of that data. So this is what Facebook just posted a few days ago. They said deepface has reached accuracies at recognizing humans that are as good as humans. 97.2% of those faces were recognized by the machine. 97.5% by humans. That's pretty much the same statistical noise, right? So you ask people, what do you think, who is this? Same answer by the machine. And they do this by rotating the head first, mapping it into some 2D plane, figuring out the distance between features, and then once you have something featurized, then you pipe it into a neural net, deep learning. So this is the stage of neural nets that we have here, deep learning, but they did some pre-processing that's super smart. And often this domain knowledge helps to do something first, and then with the algorithm take over. So Google also did something like that. They recognize cats from pictures without knowing it's a cat. So they somehow let the machinery train on data just to see that there's something like a cat in there that happens again and again, because there's lots of cats in pictures of Google. And they found that out. In one hyperspace corner there were cats, basically. There are other things that they found too, cars, tracks, but the cats somehow were something that the algorithm figured out. And the FBI also is putting $1 billion into this project, it was actually 2 years ago, to do deep learning. So this is trending. This really is trending. Literally, if you look at Google Trends, it's going up just now, right? The last year has been a revival of neural nets. And you see here, deep learning, top breakthrough technology, LinkedIn is acquiring, of course Google, Facebook are doing it, Apple is doing it, he has an iPhone, Siri is based on that, Google cars are driving themselves based on that. Nature writes about it, your deep learning, so it's all pretty hot. So that's why we do the same thing. So deep learning in H2O, how is it different from what was done 50 years ago? It's not that different. It's still using neural nets. I'll explain what that is. It's still using supervised learning at this stage. We're not learning on just data right now. We're learning on data with labels. So we need to know this is fraud, this is no fraud, 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 no fraud, and then I know what fraud is, for example. We're doing this distributed, big data. We're doing it multi-threaded, obviously, and we're doing it with all the bells and whistles of 2014. So we have the state-of-the-art algorithms to do this. initialization, learning rates, momentum, dropout, blah, blah, blah. There's a lot of stuff.
Question. So you are saying are you implementing the restrictive Boltzmann machine or autoencoder type of thing?
No,
No.
you're doing feed-forward neural nets, straightforward learning from scratch. So this is a neural net. You know, neurons, they connect somehow with dendrites and they signal stuff, axons and so on. There's signals flowing in your brain, right? Every time you see something, some signal goes somewhere, and they then send another signal to somewhere else, and they all go along. They fly all over the place. So we do the same thing, but it's just layer by layer. It's not quite as complicated as the brain. There's not billions and billions of neurons. There's only thousands or so, or maybe 10,000 or 100,000, but they're connected in a way that one layer connects to the next layer. So in this case, I want to predict whether I'm married or not based on my age, my income, and my employment, let's say. This would be a simple model. So I have 3 neurons in the beginning. They get somehow activated by my employment status, my income, and my age. And then they connect to the next layer, which has 4. So there's 12 connections. And this hidden layer that I don't see, because the user only sees yes or no, married or not, but I gave you. I don't see this stuff, right? As a user, it's just in the black box somehow. So I call it hidden layer. There's 4 neurons. They somehow get some signals, and the signal depends on how much my age was and how strong that link is. So we somehow model these connections as a double, a real number, or a float, something like that. That says how much is this connection. And then once there's some signal coming in here, all these 3, we have to figure out what that does to this neuron, and then we do the same thing again to the next layer. And you can imagine, the bigger this becomes, the more layers you have, the more complex stuff you can model with this.
So what determines the number of nodes and hidden layers?
You have to choose that. So there is some knobs that you say, I think this is a complicated thing. There must be a few thousand things in there that determine how complex my problem is. I think there's not just like yes or no in here, there's more. So you have to tune that. This is the problem and the upside of neural nets. If you get the numbers right, it's super accurate. If you get it wrong, it's not so good. So there is this problem with neural nets that you have to tune.
Are there any guidelines for selecting?
Yes. So here, this is the prediction process. So you have these numbers coming in. Let's say it's called xi. You have weights that connect this layer to this layer. That's called an uij from I to j. And you sum up the product of this times the weight. So from each guy, from the back layer to the next layer, you sum it up. And in the end, you add a bias, a constant value, because sometimes you want to have this guy always be activated, no matter what the input is. There's some like offset, right? That makes it more generic. So it's a linear model, so to speak. Something is summed up, and then you add a bias, and shift it up. But now you make it non-linear. There's this activation function. Often it's tanh, tangent hyperbolic, or as it's called in English. That thing makes something that's linear into this. So it saturates. So if you give there 1 billion, then it's still 1. If you give minus 1 billion, it's still minus 1. So you don't see much whether it's 1 billion or 10,000 or 5 or 25. It's always 1. So that's a problem in neural nets, and also the upside is kind of, it tolerates bad numbers because it's just 1. It transforms anything to 1 basically once it's out of this reach of this linear regime. But so as long as you're in here, you're very sensitive to what's happening from the previous layer. So let's say you get this number here, you sum up all the contributions from the previous layer, you get an h from that, and then you do the same thing to the next layer. So another step forward. And the very last layer, you have numbers here. Now you have to make, one more here. You have some numbers. Now you turn them into the linear sum of the previous ones, and then you don't do tanh, then you do softmax for classification. Softmax is just exponential function of that thing divided by the sum of all the others. So in this case, it's 1 divided by the sum of the 2. So together they're 1. You want to have probabilities of 1 together, right? So 20, 80 or whatever percent. That's pretty much it. So you get a number out, and you hope that that number is good. So now, what's the weight? You wonder, I could just use 0 anyway, it's not going to work, right? Obviously, you have to add some numbers. So there's other functions, by the way, activation function that are linear forever. They can blow up numerically. Right? So you have to do other stuff to make sure that the whole weights are not too big. Because if every weight gets just linearly added to the next guy, it becomes big. But maybe that's what you want. Maybe you do want to have sensitivity to big incoming weights, because this one guy is so important here that that matters. So there's things you can play. We'll get to that later.
So why yj was little bit tan h?
Why is it tan h? People like this better than the sigmoid function. Sigmoid function was from 0 to 1.
Okay.
This is symmetric around 0. And both, they have to be differentiable. So that's for one reason that we get to right now. Well, actually, the next slide. So let's say you have some weights in the beginning that are great. You end up with a great prediction. You're lucky. But normally you don't have those weights. So you have to train them, right? But first you have to start with something. So what you do, first we normalize these numbers to be standard deviation of 1 around mean 0, which means we standardize them. So all my ages are between whatever, in some range around 0, plus minus something, right? It's sigma 1. When you have categoricals like this employment, you can say I'm full-time employed, part-time employed, not employed, or self-employed. Those are 4 different factors, or categories. You can say, okay, I'll represent it as 0, 1, 0, which means I'm not full-time, but I'm part-time, and I'm also not none. And about this one I don't talk about, because by virtue of having these 3, I know what the other one is, because I can only choose one. So I know that this means part-time, and if they're all 0, then it's the last one. So you can do this mapping from things to numbers. But now we just added 4 more numbers here, or 3 in this case. Employment becomes 3 numbers. So 3 neurons instead of 1. Makes the network a little bigger. You have n things here and n things here, it's n squared, right? So it gets bigger and bigger. Which means those summations, the matrix vector multiplications, which they are, become harder to do, more work.
So did you need like high precision arithmetic here? Because some people were like 4 or 5 years.
No, not really. Usually it's so noisy and all that it's enough with floating point precision, 32 bit. So you initialize those weights randomly, but ideally you do that in a uniform weight from something to something, right, in some interval. It's not just -1 to 1. The interval is given by square root of 6 divided by the number of units here and the units before. And that's what I normalize these guys. So that's some math that you can do that tells, like, later in the next step, and you actually train this thing. How you train best is by using these weights. So that's one trick we can do to make this work better. So now how do we train this? Well, let's say I want to get, for one point that came in, this age, this income, and employed, whatever, we said, yes, married. That was the ground truth. We know this person is married. But I predict 0.8. It's not bad, but it's not right. So what's the error? Well, it's 0.2. The problem is you don't ask just here, you ask for all the points, for all the dimensions. In this case, there's only 2 classes. So it's an easy problem. You could have 50 different output classes, right? You could say, what nationality am I or something. There's more than just 2 things. So you want to get the error right for all these classes. Now in this case, when it's just classes, it's actually easy. You can say, let's see how good was my prediction for the 1 to be a 1 and the 0 to be a 0. That's called cross entropy. All you're looking at is how much am I away from the 1. If I'm a 1, my error is 0. That's the negative logarithm here, right? If I'm a 1, my error is 0. If I'm not a 1, I'm wrong. And my error goes up a lot. It goes fast, up very fast. So if I predict that there's 0, this error will be infinite. Totally wrong. This is a pretty good error function if you have to get one thing right and all the others have to be a 0. But if you say, ideally I want them all to be roughly 0, not just the one guy to be high, but I want them all to be 0. And then this one guy should be a little more, obviously, because they sum up to 1. Then you can do the mean square error, just square up those errors. So this is another error. So it's a question of what you want. You want to penalize everybody that's wrong, or just the one guy that matters most? Yeah.
So just like in the input case, you said that 3 inputs are necessary, even if there were 4 classes.
Mm-hmm.
For the output, do we really need 2 outputs, or we can just do away with 1 in this case?
You can get away with 1 in this case. So what you're doing now that we know it's wrong, right? We know how much we're wrong. I can choose either error to determine how wrong I am. We want to improve that weight. And what you do is you say my weight changes by how much I was wrong. And this is the update rule. So you take the derivative of the error with respect to my weight, and you see how sensitive am I to a weight change for every single weight in the whole network. There could be 10,000, 100,000, millions of weights. And I'm changing one weight and see how does it affect my error. So the goal is to compute this change of error with respect to a change of a weight for every weight. Now, the naive way would be to say, all right, let's do that, right? Let's take this weight, go down a little, go up a little, plot it, and take the derivative by putting a line between those 2 points, doing a differential approximation plus minus some delta, and evaluate the error every time. But that's expensive, and you don't want to do that. There's a trick to do this better. It's called backpropagation. You're doing the same thing that you did in the forward propagation when you predict it, so just go backwards. And you do the chain rule. So you can imagine this derivative to be just expanded into this, when you cross out the divide and the nets and get the yield and the u again. But in between you have these partial derivatives. So now, how does the error change with respect to the thing that was giving the error? Well, the error was determined as error of something, right? So this you can take the derivative of. Either square, mean square error, or the cross entropy. Then you have to take the derivative of y with respect to the sum that came into y. Y was the activation function, like a softmax or a tan H, or whatever it was in the way, or the rectifier, which was the straight line. There the derivative is just 1 or 0. And the derivative of the input into the activation function is the derivative of this guy with respect to x. With respect to w. That gives you x, right? It's just a linear sum. So it's all super easy now that we know that this exists. This came up in the 70s somewhere and made life a lot easier because you can analytically compute this, and this you know because these are the values here. So all you need to do is go back and just pick up those numbers that you had in the network layers. And we already fixed those weights as you go back. You don't need to compute the error out here explicitly all the time.
Excuse me.
Yes.
I think at least my guess is that we are in this problem. We are not in a convex regime. So how would the actually the convergence of the SGD on the
you can't guarantee anything. Yes.
What's your experience? Because I've not seen any SGD on neural nets before. So
Okay.
what's your experience? Is it?
It's good if you do all these tricks that you need to do. And
There are SGD for your network. For sure.
Oh, yeah.
For sure.
Excuse me. So is some genetic algorithms can be used on this, or have been used? Genetic?
I don't know. I'm sure somebody has tried that.
Okay, I mean, the algorithm used
For
in
the,
network.
for the tuning of the hyperparameters, yes. So this looks okay. That looks good. This is the. Maybe we should turn the lights off just for a second so you can see this. Is this better?
Yes.
I turn it on in a second. So this is the architecture here. So we have some weights, the implementation, right? We have some weights coming in, weights and biases, those numbers that we have to know. And at the end, we get something out. Now the question is, how do we get those out that they're better than before? Well, we did what we just said. We do this forward to back propagation for every point. But now these machines that are running this, these are the boxes here, indicated with I. This is my one node, another node, another node, another node. They somehow have this data that we said earlier. It's distributed in memory sitting there, right? So I load a file in, let's say 4 machines. Each machine has a quarter of the file, some lines of it, some rows. And they all have age, income, and these occupation status or whatever. And now we have to figure out how can we optimize those weights. Well, first you have to send those weights to everybody because they can't work on it if they don't have the weights. But initially you start with one guy that has the weights, then this guy sends it to another guy, and number 2 sends it to number 4, and number 1 sends it to number 3, so they can load balance their network communication. It's the lock tree that we call it to make this global broadcast more efficient. So then all 4 have their weights, a copy of them, and they have a quarter of the data. And now they go wild. Literally, they go hog wild, as we call it. That's the multi-threaded approach to SGD, where you just take the point, compute the prediction, make the back propagation, and fix the weights. And you fix the one weight copy of your node. So all the threads compete by updating the weights at the same time. And luckily, they don't overwrite the same number all at the same time, because there's so many things to correct. They don't all depend on each other. You get lucky, basically, that they don't read as someone else writes, and then they override it, and the other one reads, and it gets all messy. But you live with that little cost. The benefit is that you have asynchronous threads that don't lock, that can just go wild and just update as fast as they can. So you're having all these threads here update those weights in parallel, asynchronously, and you get some new set of weights, which might be slightly wrong because of this trick that you do it all at the same time, but it's a lot faster, especially if you have 30 cores or so, than if you block and say, wait, I'm busy now writing this number and no one else can touch it. You have to manage all this locking, blocking, it's too much work. So what you're doing is you let that happen, then you reduce those weights back to the one guy by summing it up, and you put it back into the KV store, so that when you reload the browser, you get that latest model displayed. That's how you do it. Or you ask through JSON, tell me what's the status, through a Python script, or you come from R and say, am I done yet? You can do whatever you want in this stage. So this is the map call, and that's the reduce call. It's the map reduce parameter.
Do you calculate the mean squared error on the entire data set, or is there a holdout? So is the whole data set running through this as you're training?
Yes, some of it or all of it. So you determine that with this mini batch, I call it mini batch, a lot of people call it also mini batch or something else. I want to clarify what that means. This means how many rows did I send through in this process globally. So if you have 1 million points in your data set, I can say do only 10,000. And if it's for a machine, everybody will do 2,500 random rows from what they have. They only have 250,000 each. In the end, you get your mini batch amount points training. And you have a new point in time that you know that's my model. Then you can score it or not. Right now, this is all done synchronously to guarantee that we know what's going on. If you do everything asynchronously, you might run out of threads to work with that, or you don't know what's going on. So in our current model, with the sizes of data we see and the number of cores people use, this is probably a good approach. So you're getting the chance to score here or here, and the scoring is the same thing as here. You also do a map call, and you say you score your points, I score mine, and in the end we sum up the result somehow to make sure that we have a global consistent number.
Sorry, so for this mini batching, is it like cross-validation? Does the algorithm ultimately end up seeing all the data, or is it just training on a random sample of the data until it has a reasonably good end?
Yes, if you do a mini batch right now, it just samples every time again. It doesn't know which ones it took how many times.
Okay.
Unless you set the mini batch to be the whole amount of data, then every iteration is a pass over all the data. There can be a holdout set that you give for scoring. Right now we don't do an out-of-bag equivalent inside this training. So this is the secret sauce, how you get higher accuracy. You need learning rate annealing. The learning rate has to go down. This was the thing that says how often did I take my gradient, my derivative of the error function with respect to the weights. As I was updating the weights, how much do I take that correction into account? If I correct every time I'm wrong and go wild, I do too much. If I say I only correct a little bit, then you get like a consensus view after a while, and you get like, okay, maybe this direction is better for this weight, a little lower, a little higher. And that's what you do here. You say, start with something big, go wild, and then freeze it in slowly. That's annealing. Then there's momentum training. It says, well, if I've changed this weight the last 10,000 times by going up a little, then I want to keep doing that. I don't want to just go down now because you're saying so. So you always go up a little bit because that's the general consensus from the past. So you can then find other local minima that way because you just keep drifting. And you can follow long valleys in the optimization path where you would otherwise step slowly along that valley. So this makes it faster, but you can also run too far and miss a local minimum somewhere. So you have to find a compromise. And that's what this ADA delta does. That's a recent Google paper that says, here's a rule how to compute the change, the learning rate for each neuron. Each neuron gets its own change based on its past. Based on how much it was changed, based on what happened to it, so to speak. And that will combine this annealing and the momentum features in one. It will be pretty smart. It actually works most of the time. You just run it and you get convergence. And it automatically reduces the learning rates as you do update in the same way over and over again. Then there's regularization. Regularization is something that you need to avoid overtraining. You don't want to just see the training set and memorize everything, and then somebody else comes along and says, well, am I? You say, I don't know, never saw you. You're totally different. You want to be somewhat forgiving to that. So what you do is you say, I penalize everything that's non-zero. Every weight that's not zero, I don't like. I only want those that really matter. That's L1. You just take the absolute value of that weight. It goes linearly, right? So as soon as it's a little bigger, you say, no, not good. I don't like that. L2 goes quadratically. So that says once they're really big, then I don't like you. But if you're small, you're okay. Dropout says, I don't see certain inputs. So my neuron sometimes turns a blind eye and says, I didn't see that. So basically you're saying, I'm training a different model at this time. This connection doesn't exist. The next time I don't see a different one. So I see another, and then there's 50% of the inputs that I miss every time a different one. So I see all kinds of different models at once. And these connections are just not there. So in the end you have an exponential many set of models that you're training at once. But of course each you only train in a little bit, in a weak way, but at least you see them all somehow. So this is a good way to get generalization error down. Then there's a way to say, my incoming weights to this neuron, altogether, they're too much, they're more than 100, I don't like that, so scale it back to 100. This way you can deal with the linear regime thing, where the activation function was going up and up and up. You can say, that's fine, I don't mind you going up, but once you're too big, I scale you down. This is good for the rectifier. And then there's this bridge search capability and the mini batch stuff where you can actually try many, many things, tune the parameters, and then at the end you say, that's the best one, I want to continue training that. You have this checkpoint capability.
Yeah, one question about the last part. So all those regularization tricks,
yes.
should I just use all of them? Do they compete against each other? Are they complement each other? What's your experience for using those?
Usually it's best to use most of them, but maybe not L1 and L2 at the same time, or make sure that you're aware of what you're doing. So you want to basically always do a grid search. That's the best thing. So I have a rule book at the end where I say how you should do it. But it's good to use one or the other. Certainly L1 or L2 is a good thing. Dropout is a good thing if you want to have generalization error low. There's max sum weights is good when you have the rectifier. But for 10H you don't need that because 10H self-limits. And yeah, so it's okay to mix them. So this is the application, MNIST. So you have handwritten digits. This is an old data set. You have 28 by 28 pixels for each one of those. And 255 or 256 levels of how black it is there. So you digitize it and say, okay, it's gray, it's white, it's black. And you end up with these 784 dimensional points, 60,000 of them, that have 10 class labels, right? I'm a number 3, I'm a number 5, I'm a number 6. And you train that, and then you're trying to predict on a separate set of 10,000 points what each one is. And of course, you can tune this forever until you publish your paper and say, I got a good number. And that's what people do. They run this for weeks and weeks, get one good number somewhere and say, I found a better one. So this happened. This is the numbers here in the past. This is a little bit small to see. 4.7 percent error on those 10,000. Then it came down to like 2, 3, then 1, and then 0.83. This 0.83 is the best right now without doing any transformations here. If you take this thing and deform it, elastically rotate it, scale it, skew it, then you can do more. But if you just take them as they are and say predict, and use that as input features, the best you can do is 0.83. That's with fine-tuning by the Microsoft paper that just came out a year ago or so. Deep convex networks, 0.83. They don't fine-tune, they get 0.95. So about 95 wrong out of 10,000. Pretty good.
So what are the features represented? 784 columns.
Yeah, 28 by 28 pixels. So it's really just pixel color for blackness.
And that's the number of the input neurons.
Yes, correct. That's the number of the input neurons. And the output neurons are 10. So 0.83 is the best there is. 0.95 without tuning, and everybody else is 1% or more, right? So we get 0.95, which is good. This is as good as it gets. This is too small. You'll get the PDF version. You can see these are all the actual parameters used. Took 7 hours on one machine to get there. If you want to really get to 1% or something. If you want to get to 0.95, it takes maybe 20 or 40 or 50 or 100 hours, whatever many machines you have. So it's a pretty big effort to get down to that number because the training error is always 0. You already saw everything. There's nothing to see anymore. But your regularization tricks, this blinding out stuff, changes you so that sometimes you get lucky when you test on that test set. So you're basically just tuning for the test set to get a low number right now. It's almost like cheating, but that's the lowest you can get. It's like this fluctuation of the 1% range. Or 0.8 if you're really lucky with this other thing. So I would say this is good enough. If you look at the confusion matrix, these are the actual numbers, these are the predicted numbers. Sometimes you're not on the diagonal, sometimes you're wrong. The ones that are wrong the most often are here, 7 and 2. So the actual 7 was mistaken for a 2, which means this thing here is not right, like a 2, but well, I guess it makes sense. 4 is mistaken for a 6. Yeah, yes, you can see that if you're writing it fast, right? And 4 is also mistaken for a 9, which is almost trivial to see here. That's actually the highest number. That's 7 wrong. So all this makes sense. It's all good. So we can move on to the next data set, this prostate data set. There is 9 variables. One is just an ID, so you omit that because it doesn't mean anything, which number you are. That's the number in the database of these 380 people. Then there's whether or not you have tumor in your prostate. It's only for males, obviously. Then what age you were, what race, whatever, some other exam, how much of something else is there, how much prostate-specific antigen value you have. The PSA, that's some famous number. Or famous thing, everybody knows that PSA thing, but doctors now even say if it's high, don't worry, it's okay, you don't want to misdiagnose it or not.
Remember, right, this is a wide data set, isn't it? It's a wide data set, many more columns and rows.
It has 380 rows and 9 columns, so
9
it's
columns.
pretty long. Yeah. It's not big, it's super tiny actually. Then there's some Gleason score, so that's just a data set. People use it a lot. So let's do this now in life, in real life, right? Let's go here. Let's run deep learning on the prostate data set. Let's try to predict capsule. That's the second of the things. Let's ignore ID because an ID doesn't mean anything. Yeah, we want to do classification. Let's use 10H. And I'm telling you that 10 by 10 by 10 neurons is enough. Super simple network. And let's train 10,000 times over those 380 points.
And this is 10 hidden layers?
3 hidden layers, each has 10 neurons.
Okay.
And mini batch will be adjusted down to 380, even though I say 10,000, it doesn't mean anything. So every time we go through, we have an opportunity to score. But the scoring thing is determined down here. There is some score duty cycle and so on that you can set, but this is expert level stuff. You don't need that usually in the beginning. You just press OK here. And now this is running. So let's see. Well, here is an ROC curve that you can move around, and you see your confusion matrix change. Oh, it's already good. And you see if you had, who knows what this is, ROC curve? It's not the easiest thing, but it's okay, right? You can say, how many did I get right, how many did I get wrong? And you want to be up here, everything right, nothing wrong. Depends on your threshold. So if your probability is something like, here it says 0.74. So probability is more than 0.74, then you have cancer, basically. That's what this says. And if you do this, you get it pretty much always right, except for 2 actual cancers that are misdiagnosed as saying you don't have cancer. Too bad, right? That's not good. But this is this run. It came down to 0.5% error. And we can do this again. It will be the same thing, more or less, up to this randomness of the threads competing with each other, updating the same weight matrix. So next time it's going to be slightly different. In fact,
so what is the convergence criteria that you?
I said once you're 0, you stop. But in this case, we didn't reach 0, so it stopped and it ran out of time to out of epochs to run. I said 10,000 epochs, which means 10,000 times through the data set. So this is just to show you that this works. Here in the slides, I got a 0 error after 10 seconds. And you see 10, 10, 10 units in these 3 10H layers, which means it's 7 times 10 is 70, first matrix, then 100, then another 100, and then another 20. Plus the bias values, 10, 10, 10, 2. There's no bias for the input. If you add that together, you get 322. So 322 numbers, floats. I can predict everything right. From a data set with 380 times 9 things. So there's like 4,000 things in there in that table. But with only 300, you get the gist of it, basically. Overfitting the training set doesn't mean much anyway. You can always overfit the training data if you have a complex enough model. But this is pretty impressive to get to 0 error with fewer, right? It's a good thing. So now your next thing, which is grid search. So let's try that. Grid search means that you're saying prostate, let's predict, for example, age in this case. Let's do a regression problem. Regression means instead of saying which class am I, I'm saying how old am I. Let's say 37.3 or something, any number. Again, I ignore the ID. I say no classification. And now I'm training either with 100 by 100, like 2 layers of 100, or 5 layers of 50, or 7 layers of 20. Let's say deep learning, right? This is deep learning, many, many layers. And that gives you the capability to represent nonlinear functions, which we say, how can the age possibly depend on all these things? How do we model that? It's not easy. Now let this thing figure it out. So that's everything as its default. Let's say go. Now we have a grid search progress report that says here 100 by 100, 50, 50, 50, and 20, 20, 20. Let's see what they give. And if we go all the way to the end, you're seeing the prediction error. That's the mean squared error. So for every of those 380 points, we're looking at how well did we get the age right. We square up those errors, and then we take the average. Mean squared error. So 20 years off is pretty bad. 40 years off. So the years in this data set are 44 to 79 or something. So it's typical, male age that has prostate problems, fortunately. So this is training right now. Let's see what happens. There's all these other things that you can see. So you see that neural nets has a lot of options. There's a lot of features that you can give. And that's the downside, but also the upside. If you know what you're doing, you can get a really good model. And if not, then you might rather use a random forest or something, or a gradient boosted tree. So it's a take and give, basically. But this is really good for many, many output classes, because it can figure out, just like linear regression, just more complicated to figure out those connections back. Okay, so now we have a winner. Let's take the first one here, the winner. This was the one with 50, 50, 50. 10H, you see the weights here, and the biases, mean and random RMS, mean square values, so there's some diagnostic. You see the variable importances, PSA, prostate-specific antigen, is the number one thing determining this age from your numbers. So if you have cancer, you're probably old or something, that's what this is saying. Those things are not entirely super duper, right? This is noisy, you can get slightly wrong numbers, so it's an unsolved problem how to get the feature importances. And I got this feature importance computed by the best paper there is. Actually, I had to send an email to the author himself, so thanks for that. If you ever see this talk, Dr. Gideon. Here you see the history. So we only did 20 seconds. Now let's continue this, because you know this is the most promising model, most likely. Let's add another 10,000 epochs, and it will just continue. We should just add new rows here. So 48, okay, we continue. 12, it's going down. And this is how you do neural net training, right? You do a grid search, you see what's promising, and then you continue. And then maybe you say, okay, it's not the best thing, so I'll do some more. We're working on better grid searches that are not just orthogonal, what is called a cross product of all these things, but some randomness and all that, but it's all still on the to-do list. But there's better ways than to just do what you say. I can actually do my own guess based on Monte Carlo principles, and my multi-dimensional integral over the sample space will be better if I do random instead of you telling me here, here, here. So now it's going down to 6 and so on. And if you wait long enough, it will be below 1.
How do you know when to stop?
Yes, that's a good point. So you can just show me this plot here. There's a plot, and you see that it's going down. Oh, it's still reloading. You have to stop the reloading by here, clicking on this. So once this doesn't go down anymore, you can say I'm kind of okay. You can also specify a stopping criterion in the beginning, but that's just the absolute number at which to stop. When the training error is below that, you stop. This might be helpful for grid search or something to see who got there first.
How do you know you're not overfitting?
In this case, you are overfitting because there's only a training data set, nothing else. So this definitely overfits. There's no regularization done or anything. In reality, you would also add a validation set, and then you will see this validation error, and then you will see that that actually goes up again after you start to overfit. And you will see only the validation sets MSE here, so you actually see what matters, not the training. So let's see how good we are now. If I keep looking. 3. So yes, this will eventually get better. As you can see. So let's go back to the talk. So in this case, I ran it earlier, and I got in 1 minute, 10 seconds, I got to 0.95 error. So that means your age, I can tell within 1 year, basically, squared error, which is the same for 1 year, it's linear or squared. So 1 year error on the age on average from this other measurement. Of course, it's somewhat overfitting here because there's a lot of parameters. That's expected, right? You should be able to get that error. So now we have the live demo of the eBay data set, which is a lot bigger than anything you've seen in this talk so far. So guess what they are doing at eBay? Well, they're selling something. They're typing in a description. They're saying, my shoe has amazing looks, whatever. It's amazing. It's the best. It's the best. And you have to guess what it is as eBay, because if they put that shoe under electronics, it's not going to be sold. And then they don't make their fee, their commission. So they're trying to optimize the placement of those items when they're being sold to the right place. They're trying to help those people. Then they type in, my shoe is amazing, it's shiny. Then you have to immediately tell, okay, that's a woman's shoe or something. It has to go into the luxury section for fashion designers. So how do they do that is they take their word vector, binarize it, like I use the word amazing, I use the word shoe, I use the word shiny, and they put that into an SVM-like format which says, actually it's a woman's shoe. They take what people said it was for this data set, which might not be correct, but they take what, in this case, for this data set, that's what they gave us. Thank you for that. eBay receivers. They take this label that the human said, they say, okay, position 3 is a 1, position 9 is a 1, position 13 is a 1. That's a sparse representation. They give us that file and they say run, basically, and tell us how good you are on this test train split. So the training data set has 500,000 rows, 8,500 columns. There's a lot of words you can choose when you type in something. And 467 classes. This is only for jewelry and watches. So it could be an Omega, could be a Rolex, could be a diamond, whatever. So you have to figure out what it is from that, right? And H2O, because it has this compressed columnar store, it doesn't need this times this plus this times this. That's 5 billion floats or doubles or something. It only needs 60 megabytes. So it's super tightly compressed because it's mostly zeros. And as you parse this data set, it never gets expanded. It's always small and it stays small.
Excuse me.
Yes.
So when you optimize during that SGD process, do you, your update state also sparse, or so there is a version of sparse, and probably you know that as SGD, sparse update, so you are a function of sample dimensionality, not problem dimensionality.
Right.
So
we're working on that.
Okay, great. Yeah.
So I'll show you maybe first before we get here, I'll show you the actual run. I just launched this a while ago. Actually, when was that? It was 2 hours ago. It's still running on 4 nodes. So let's see this cluster. If I go to the cluster status, it's very busy. So this right now means that all the threads are working hard. And when we update the website, they're competing with the threads that are actually working. So this model is so busy with all these neurons being updated that we are competing. The web browser competes with the actual model because both are in Java. So we have these 4 nodes, and they're all working with 32 cores each. Okay? So if you go look at what happened, so we have 1.8 million model parameters. That's a small neural net model. I just used the default 200 times h times 2. So all I have is 400 neurons that have to figure out how these 8,000 input things get mapped into the 500 output classes. It's not easy, right? And what we get now is 17% error to get it the right one, exactly the right class. Right? But that's a training rate. On the validation set, it's half-half. So every second I get exactly right out of those 500 classes. And let's go down first, and I'll go back up later. The browser is a bit busy here because it's sending over 8,000 names for all these colors. So here, this is the hit ratio. This means how often did I get the first one right, the highest probability I predict. Half the time, as I said, that's on the validation set. But if I check the first 10, then I get it right 65% of the time. So it's still not great. It's still not getting a lot better, even if I look in the first top 10 predictions. But it's better than 50%, so you get better the more you have. And if I had the top 500, I would get to 100%, obviously, because I get them all. So we have this hit ratio computation built in. If you look at the scoring history, you see that the training data set, it's 17-18% for a while now. It's not getting that much better. It started at 100% error and came down to 20 or so fast. So after 1 half hour to an hour, it was at 80%. But the validation set error is just not that great. It's just 50, 50, 45, maybe if you're lucky 43, 40 even here. It was 41, so I can say it's 40. So now what you would do is you would add generalization error improvements, which means generalization. You would add dropout, you would add a run penalty, you would make a bigger network, you would not use 200, 200, you would use 1,000, 1,000 or something. So that's where it gets interesting. So we're working with eBay on this to make this actually better. This is just for you guys to see that this actually can get decent results in 1 or 4 machines, something anybody can buy. You see the accuracy drops off rather fast in the beginning. So all you really need is the first 5 minutes. The rest of the 2 hours, you don't really need, because this tells you that this model wasn't that great. We're saturating here at 20% or 50%, depending on which test set or training set you're looking at. And if you see that you're only at 20% for the training, 50 for the validation, that's not good. You want 10% validation or something, right? You want to get it right 90% of the time. Otherwise, it's not going to make money for you. So this is how it works. These are the tips. Yes.
Where did you get the data set?
From eBay.
You crawl it, or you just they have a nice format?
Customers.
Oh, okay.
So these are the tips in general. So if you want more layers, you can afford that, you get more complex functions. If you have no layers, you have linear regression. If you have some layers, you add something more complicated in there. If you want to do a exclusive OR or so, you can't just use one layer. So you have to do something more. So I would say 2 or 3 or 4 layers makes it interesting. If you add more neurons, then you have more things that see what's happening, so you get more fine structure to data.
So what's the most number of neurons you've trained on? That Google Cats example you gave was like 5 billion neurons or something?
They have 5 billion parameters, I think.
Parameters,
It's
okay.
model parameters.
Model parameters. So how many have you trained on?
Matrix, it's the number of units. So we've done 10,000 or so. Of course it gets slower because you don't use GPUs. At this point we're not using GPUs yet. GPUs are really good for this matrix vector multiplication. The problem with GPUs is they don't store a lot of data. If you want to work on a terabyte of data on a cluster that's on Hadoop, how do you get it onto the GPUs? So that's a problem. So we can run this on a 100-node cluster on your Hadoop cluster, and you can just launch it. And it might be 5 or 10 times slower, but it will get the results. And until Intel or AMD does something, then the GPUs will be faster. But they're both working on making those more powerful processors that can do these operations. So I'm very hopeful that they can do something. Or maybe they'll add GPUs ourselves. It's not yet clear what the path is, but it's certainly doable. And actually, we've done it before. So
is that when, sorry, just
yeah?
one other follow-up. Is that when you would do things like structure learning? Because what you showed is basic neural nets, right? It's not kind of the same thing as what you were talking about earlier.
It's deep belief networks, right? It's the same thing that Hinton's doing now. He's saying you don't need the restrictor Boltzmann machines. You just need a good neural net with the right tricks that you do all these initializations, the automatic learning rate, the momentum, the annealing, and so on. What you can do is you can learn layer by layer based on the data without having the labels. And at the very end, once you have the structure right, then you add the labels and you fine-tune the software and so on. That's all things that people do. But the last 3 months since I joined, obviously we didn't have time to do everything yet, but this is what we have for now. And it's all open source. If somebody has an idea how to improve it, we're welcoming them for contributions or at least suggestions. But there's no secrets, right? This is all, the math is free. So more regularization gives you better validation error, generally, unless you do too much. If you say, I don't want any numbers to be non-zero, then of course it's also not great. Do a grid search first, get a feel for how it converges, because most of the time you get random noise if you have wrong parameters. NH is the most solid one because it keeps it at -1 and 1, doesn't blow up. Rectifiers like this maximum weight squared that's incoming, so that you make sure that they don't add up to too much, you normalize it down. Rectifiers also like the L1, basically saying these guys don't exist, so they don't add this linear term that's going up. Dropout always helps, because they're just making you blind to something, so you get more robust. This thing doesn't always have to be there for your model to be good, basically. When it's distributed, your mini batch size, the amount of points you go through before you synchronize again, determines how often your model gets updated. So the more often you update, the better the model, but the more price you pay in your network cost, right? Because you don't have InfiniBand, you have only 1 gigabit for it. So you're paying the price there high, or maybe it's worth it. So you have to try that. Then you have eta delta, this automatic learning rate thing. Try these parameters. If you don't have that, try these learning rates, these annealing factors, and the momentum values in the beginning at half and go up all the way to 0.99, which means it's super strong momentum, really fast, flying all over the place. And the learning rate is low. there's a ramp from here to here, how long it takes you for the momentum to change from initial value to the last, to the end final value. That ramp time can be in something in the order of the annealing time for the learning rate. They can go hand in hand. They don't have to, but I will try that. That's just a guideline how to get better results. If you have imbalanced classes like fraud or no fraud, usually that's not one-to-one, right? So you can do balanced classes equals 2. They'll do oversampling of the minority class to balance it, so the thing gets more, it sees more of the fraud. And then there's load balancing. You can force if you have a small data set that doesn't have enough data to actually run on 10 machines. You might want to force that distribution a little more than what you have by default. But these are all tricks and tips. So in summary, H2O works, it's distributed, it's in memory, it's fast. You can do great machine learning with it. It's easy to use. I can use it, and I even have to write Java for that, right? And it's really not that hard. Neural networks are back. They have been gone for a long time. People thought SVMs are better. They might still be better in some cases, but SVMs are just one particular type of neural net, some perceptron that separates boundaries. This can be more generic. This can be a lot. This can do anything basically. It can drive cars. It can probably do a lot more than check number recognition, right? So you can try it yourself. You just type this and you'll get H2O on your machine. And as long as you have Java, you can run it. Windows, Linux, Mac, doesn't matter. That's it.